Welcome to the session of electronic devices gate subject. Here we will be dealing today with a topic called diffusion current. In last class we have dealt with a topic called drift current, and we have learned various formulas regarding current density, resistivity, mobility, rho, which is a value, and also the relation between resistance and resistivity, relation between conductivity and resistivity. So all this we have learned, and we have solved even some problems also for drift current. Now let us go with diffusion current, which is an opposite to drift current. As in drift current, I told you there should be a uniformly doped semiconductor taken, and the applied external electric field should be there. But the opposite to diffusion current is drift current is diffusion current, where you need to take non-uniformly doped semiconductor. So the following points you need to remember here. You need to take a non-uniformly doped semiconductor. Non-uniformly doped semiconductor and no applied electric field. No applied electric field. No external electric field is applied here. No external electric field. Whereas in drift current, we are applying external electric field, and also we are taking uniformly doped semiconductor. So these are the two important differences between drift and diffusion, and you need to remember these two important points carefully. Okay. So here I am taking non-uniformly doped semiconductor. See the structure. This is a non-uniformly doped semiconductor. You can see from this point to this point, it is heavily doped, and from this point to this point, it is lightly doped. And as you go, as distance increases from left side to right side, the doping concentration is very less. It has been decreasing. Here there is no doping concentration in this gap, whereas in this gap there is only one charge. Here also there is only two charge carriers are doped. So this is as distance increases from left side to right side, this charge carrier's doping concentration is decreased. So this is what called as non-uniformly doped semiconductor. It's called as non-uniform doping. But even though it is non-uniform doping, here I am taking a p-type semiconductor here. So assume this is a p-type semiconductor, and majority charge carriers are holes. These are all holes which are having a positive sign here, which are having a positive sign, positive sign, positive sign. And remember, all positive signs are closely attached with each other. If they are closely attached with each other, they will get bombarded with each other because they are having same sign. They are having same sign, and they will bombard and they will repel with each other. They will not attract because they are not having a different sign. They are having same sign. So they will repel with each other, and they will move from higher concentration gradient to lower concentration gradient. Means higher charge density, higher carriers, which are having a place with the higher carriers. This is a place with the higher carriers. This is a place with the higher carriers, and this is a place with the low charge carriers. And a gap is there. A lot of gap is there between this one. So therefore, charge carriers will definitely move from left side to right side because they get repelled with each other because of they are having the same positive sign, and therefore they will settle in free space here. They will move towards free space. So here they themselves are moving from one point to another point. So therefore, as you studied already earlier, if a charge carrier is moving from one point to another point or from one position to another position, immediately current is generated in the device. So here they themselves are moving from one point to another point, all these charge carriers, so immediately current is generated in the device. That current is called a Hall current. And that current, it is due to uh, diffusion of charge carriers. So therefore that current is called diffusion current. So this process is called diffusion actually because the charge carriers are diffusing themselves from one point to another point. So therefore in turn creating the current. So this current is called diffusion current. And here this is the higher concentration gradient, and here lower concentration region, and this is a non-uniformly doped semiconductor. Likewise, diffusion current is generated. Now you can observe here, if you draw here, if you assume this is a zero axis, and this is the concentration of charge on y-axis, and it can be drawn a graph like this. This is y-axis and this is the x-axis. Assume x-axis is the distance, x is equal to 0 here, and this is the concentration of charge. What I am taking, it's a positive p type hole. Holes are concentration of charge, so therefore p I am taking here, distance x I am taking. What happens? You tell me at x is equal to 0 distance. At x is equal to 0, what happens? This is x is equal to 0. At x is equal to 0, how much concentration is present? Large concentration is present because it is heavily doped. So therefore, I can say that this is a large value at x is equal to 0. And as distance is increasing from left side to right side, what happens to charge carriers? It has been decaying. So therefore, I can say that charge carriers are slowly decaying like this, slowly decaying as distance increases. So this is what the graph for this diffusion current. Diffusion current. Now you can take the slope of this one actually. What is the slope? This is the y-axis and this is the x-axis. This is called slope. What is slope is given by always slope is equal to dy by dx. Slope is equal to the general formula is dy by dx. But what is the term we are taking in y-axis, which is nothing but holes. So therefore slope can be written as d, instead of y I can write p, and instead of x I can write x, which is a distance. Here x is a distance and p is concentration of holes. P concentration of holes, p concentration of holes, and x is a distance. X is a distance. What is actually differentiation here? Here d by dx is not is this is we are taking d by dx because it's a slope. So what is the original meaning of differentiation means? It's a decrement function. Differentiation is nothing but a decrement function. Decrement function. What is decremented here means p. What is p? Concentration of holes. So holes are decremented. Holes are decremented from x is equal to 0 to x is equal to some value. Holes are decremented, right? So this decrement function here, holes are decremented means concentration. Holes are said to be a concentration. So therefore this by dx can be written as concentration gradient. Concentration gradient. Concentration means charge carriers. Gradient means decrement. Gradient means decrement. So therefore concentration gradient can be called it as dp divided by dx. dp divided by dx. This is what called as concentration gradient, and it is been decaying from left side to right side, right? So this concentration gradient is existing here dp by dx, and holes are moving from one point to another point. From this point to this point, holes are moving. So therefore, as current is exists, current density also exists here. You need to remember here one point, current density exists here. What is that current density? Current density due to holes, so it is given by Jp. Current density is directly proportional to what means concentration gradient dp by dx, because holes are moving through gradient only. So therefore current density due to holes is directly proportional to dp by dx. So a simple formula exists, Jp is equal to E, charge of the carrier, E into dp, diffusion constant of holes, into dp divided by dx. So if you remove this directly proportional, then you will get Jp is equal to E into dp by dx. E is called charge, dp is a diffusion diffusion constant of holes, diffusion constant of holes, and dp by dx, concentration gradient, right? Now here, can you tell me concentration gradient dp by dx is always a decrement function? So always it decays. It is decaying means it is given by negative sign. It is decaying means it is given by negative sign. But what is the charge of these holes? Charge of these holes are positive. Positive. Charge of the hole is positive. So to make a positive, already we have negative. Negative we have already in the form of dp by dx, we have negative because it's a decaying function. So to make this charge of a hole a positive, here I am adding one minus sign here. Minus E into dp into dp divided by dx. So this is called current density due to holes. current density due to holes. So current density due to holes, you will get a minus sign there. Why minus sign means in order to overcome the decrement of dp by dx, which is a decaying function or concentration gradient. In order to overcome that one, then we are adding minus sign so that minus of this decrement function is positive. So therefore this is that is the charge of a hole. So therefore then it will become as jp is equal to minus e into dp divided by into dp by dx. Right? Now similarly, can you tell me what is current density for electrons? What is current density for electrons? If it is n-type semiconductor, previously we have taken this one as p-type semiconductor. Suppose if I take n-type semiconductor, what are majority charge carriers? Electrons. Wherever you see left side is heavily doped because it is a non-uniformly doped semiconductor. So as distance increases, only few electrons will be there here. So this is electrons. More charge carriers are there electrons. All electrons will have negative sign, so therefore again they will diffuse from one point to another point, so in turn creates a current. So this is n-type semiconductor. Now tell me what is the formula for n-type semiconductor? Current density for electrons is equal to, anyone? J suffix n is equal to huh? E instead of dp, dn
by dx.
dn divided by dx. Actually, what about this minus? Actually, minus will be there here. The same formula I'm writing, see here. Minus e dp by dx. Here minus e dn into dn by dx. But what is the charge of electron? It's a negative or positive? Negative. Charge of electron is negative. Already minus is there. Minus of minus becomes plus. Minus of minus becomes plus. So the formula is plus e into dn by dx. Plus c into dn by dx. So this is a very important formula. Sama. Jp is equal to, remember, minus exists for holes and positive exists for electrons. Jp is equal to minus e dp into dp by dx. Jn is equal to plus e dn into dn by dx. Very important formula. Sama. This is the current density for holes and this is the current density for electrons. Okay. Or you can write the other formulas also like this. Most probably in gate exam they will be asking like this. Jp is equal to minus e into dp into, this can be written as differentiation of p, means you can write this one as p2 minus p1 divided by x2 minus x1. Similarly, Jn also can be written as Jn is equal to plus e dn into n2 minus n1 divided by x2 minus x1. n2 and n1 are two concentrations of electrons. p2 and p1 are two concentrations of holes. x1 and x2 are two distances. x2 and x1 are two distances. So if it is given in the problem like this, then you can apply these formulas also. Jp is equal to minus e dp into p2 minus p1 divided by x2 minus x1. Jn is equal to plus e dn into n2 minus n1 divided by x2 minus x1. Right? So this is regarding diffusion currents and their current densities. And even they will ask to find current also. So while they ask to find current, what happens? Suppose holes, this is current density. What is the formula for current density? It is ip divided by a. Current divided by area is current density formula. So minus e into dp into dp by dx. So what is the current? Current is equal to, what is the current? Current ip is equal to a, cross multiplied, you get minus a e into dp into 2 dp into dp by dx. Likewise, you can find even currents also, whole current. This is called whole current. Similarly, for electron current also, In is equal to plus ae dn into dn by dx. Or you can use this formula also. This formula will appear like this. ip is equal to minus ae into dp into P2 minus P1, P2 minus P1 divided by X2 minus X1. Okay. Likewise, various formulas exist. While you practice all the problems, then you will be very much thorough with this diffusion currents and their current densities and their currents. Okay. Right. Next. Let's go with another topic which is called Einstein's relation. You might have heard about Einstein's relation at constant temperature. At constant temperature. At constant temperature, the ratio of diffusion constant of holes. The ratio of diffusion constant of holes. Diffusion constant means P. Diffusion constant of holes to mobility of holes mu P is a constant. That constant is equal to Vt, which is called volt equivalent temperature, where Vt is called volt equivalent temperature, and dP is diffusion constant of holes. dP is diffusion constant of holes, where mu P is mobility of holes, right? Vt is volt equivalent temperature, dP by mu P, or you can write again the same formula as dN in n-type semiconductor divided by mu n is equal to a constant. That constant is equal to how much? Vt, where Vt is volt equivalent temperature. Now similarly, Vt can be written as Vt is equal to Kt divided by Q. Vt volt equivalent temperature, Vt is volt equivalent temperature. That Vt can be written as Kt divided by Q. What is K? Mute your voice, all of you. Mute your voice.
So
V.
please type your request, sir.
Huh?
Request accept.
Acceptance, huh?
Yes, sir.
Only one fellow, no? Sivanagumani. Okay. Vt is equal to Kt by Q. What is K? K is called Boltzmann constant. K is called Boltzmann constant. A famous scientist, Boltzmann. K is called Boltzmann constant. What is the value of Boltzmann constant? It is equal to 1.38 into 10 power minus 23 joules per degree Kelvin. Joules per degree Kelvin. Q is called charge. Charge is given by 1.6 into 10 power minus 19 coulombs. Substitute all the values here. K 1.38 into 10 power minus 23 into capital T in degree Kelvin divided by 1.6 into 10 power minus 19 coulombs. So final answer you get capital T divided by 11,600. Please do remember this point. Capital T divided by 11,600. So here this complete answer equation is equal to capital T divided by 11,600. 11,600. dP by mu P, that is equal to dN by mu N, that is equal to Vt, that is equal to Kt by Q, and that is equal to a constant which is T by 11,600. So you can use directly formula now. You can use different ways. dP by mu P is equal to T by 11,600, or dN by mu N, that is equal to T by 11,600, or Vt, you can write Vt directly as capital T by 11,600. Okay. Now for example, at room temperature, what is volt equivalent temperature? At room temperature, capital T is equal to how much? 27 degrees C is the room temperature. You need to convert into Kelvin. 273. How much? 300 degree Kelvin. T is 300 degree Kelvin. What is Vt? Vt is equal to capital T divided by 11,600, that is equal to 300 divided by 11,600. Both gets cancelled. If you simplify it, what answer you get? 0.026 volts. That is equal to 26 millivolts. This is the most important point. Volt equivalent temperature Vt at room temperature is 26 millivolts, or it is equal to 0.026 volts, right? So now you can see here mobility using this equation. Diffusion constant is directly proportional to temperature. Various points you need to learn here. Mobility is inversely proportional to temperature because 1 by mu is equal to T. So therefore you can say that here mobility is inversely proportional to temperature. This is one point you need to learn. Diffusion constant is a constant and it is directly proportional to temperature, but here mobility is depending on a value, so therefore mu is inversely proportional to temperature. As temperature rises, mobility decreases. Temperature decreases, mobility increases. So there should be a relation between mobility and temperature, which is nothing but this one, right? Even in last class we have learned some certain relation like intrinsic concentration is equal to A naught T cube e power minus Eg naught divided by Kt. So intrinsic constant Ni square is directly proportional to T cube, and you can write this Ni is directly proportional to T power 3 by 2. T power 3 by 2. Sir? Sir. Yeah. So here what happens is mu is inversely proportional to temperature. Please take care of this one, right? Next. So this is called as Einstein's relation. So please do remember all these formulas now. So take this formula. Assume electron charge Q is equal to 1.6 into 10 power minus 19 coulombs. Kt by Q is equal to 25 millivolts. And electron mobility mu1 is equal to 1000 centimeters square per volt second. If the concentration gradient of electrons injected into a p-type silicon sample is 1 into 10 power 21 per centimeter per 4, Magnitude of electron diffusion current density in amperes per centimeter square is dash. Magnitude of electron diffusion current density in amperes per centimeter square is dash. Please do the problem. Write given data first. Q is given, Vt is given 25 millivolts means room temperature. Room temperature. Mobility is given mu(n) 1000 centimeter square per volt second. Concentration gradient of electrons injected into a p-type silicon sample is given. dN by concentration gradient of electrons means dN divided by dx is concentration gradient. It is equal to 1 into 10 power 21 per centimeter power 4. The magnitude of electron diffusion current density is magnitude of electron diffusion current density. So what is diffusion current density of electrons? Jn. Jn is equal to plus E dN into dN by dx. You take the value of dN. dN is not given, so take the value of dN. The value of dN is dN is not given. You need to find it, right? So how to find it? Tell me. Jn is equal to E is given 1.6 into 10 power minus 19. dN you can find it because mu(n) is given, so you can find dN. What is the formula? According to Einstein's relation, mu(n) divided by dN by mu(n) is equal to dN by mu(n) is equal to Vt. So what is dN? dN is equal to cross multiply mu(n) into Vt. What is mu(n)? 1000 into Vt is 26 millivolts. So 3 10 power minus 3. dN is equal to 26. Substitute it. 26 into dN by dx is 1 into 10 power 4. 21. Sorry. 10 power 21. So how much? Jn is equal to how much? Find the answer. Answer ma?
4160 amperes per meter square.
4160 amperes per meter square, right? So like this you need to do dn, you need to find it. Okay,
Sir,
next. Ah,
sir.
ah,
Sir, mu n is equals to 1000 centimeter square, sir.
yeah.
Silicon sample is given unit centimeter power 4 ఇచ్చినాడు కదా సార్.
ఎక్కడ?
ఇక్కడ సార్ సిలికాన్
that
శాంపుల్ ఈజ్
is dn by dx కదా. That is dn by dx.
అంటే సెంటీమీటర్ పవర్ 4 ఉంది కదా సార్. అంటే
అవును.
దానికి రిలేషన్ ఏమన్నా క్యాన్సల్ అయ్యే అట్లా కూడా ఉంటాయి కదా సార్.
ఏం అవసరం లేదు, మనకు డైరెక్ట్గా యూ హ్యావ్ కరెంట్ డెన్సిటీ ఆంపియర్స్ పర్ మీటర్ స్క్వేర్ కదా, సారీ సెంటీమీటర్ స్క్వేర్, దిస్ వన్ ఈజ్ సెంటీమీటర్ స్క్వేర్ బికాస్ ఆల్ ఆర్ గివెన్ ఇన్ సెంటీమీటర్స్ కదా. సో ఆల్ ఆర్ గివెన్ ఇన్ సెంటీమీటర్స్, సో దేర్ ఫోర్ ఇట్ ఈస్ ఆంపియర్స్ పర్ సెంటీమీటర్ స్క్వేర్. ఓకే,
ఓకే
డోంట్ క్యాన్సిల్ అవుట్ లైక్ దట్.
ఓకే సార్.
You just simply write what are the final units of this,
ఓకే
isn't it? So finally what do you need to find? Current density. Whatever you substitute all this, you get it cancel, ultimately you get at last units are amperes per centimeter square if it is given in centimeters, or if it is given in meters, then you will get amperes per meter square. Okay
సార్.
right. Here that is also right, no problem. Actually what is the concentration dn? What are units for dn? 1 by centimeter cube or 1 by meter cube. Already distance is there. What is distance? 1 by meter. So 1 by meter cube into meter, how much? Meter power 4. Or if it is in centimeters, 1 by centimeters into 1 by centimeter cube. So what do you get? 1 by centimeter whole power 4. Okay. So that is concentration gradient units. 1 by centimeter power 4 or 1 by meter power 4. Okay. Right.
ఓకే సార్.
Right. Next. At T is equal to 300 degree Kelvin, the whole mobility of a semiconductor mu p is given, kT by q is given, the whole diffusion constant in centimeter square per second is dash. I told you after point you need to go for 2 digits only, so please be careful. After point you should remember 2 digits. That 2 digits should be in a correct manner, otherwise your answer will may go wrong. Whole mobility mu p is given, mu p is equal to 500 centimeter square volt second. Vt is given 26 millivolts, 0.026 volts, or whole diffusion constant dp in centimeter square per second you need to find. So check all are in centimeters or meters. So all are in centimeters, so no need to worry. Then what is the formula? Oh, dp by mu p is equal to vt, or that is also equal to t by 11,600. So dp by mu p, how much? dp is not given, divided by mu p 500, that is equal to vt. Vt already given, it is 26 millivolts. So dp is equal to 26 into 10 power minus 3 into 500. That is equal to 26 into 0.5. How much? How much? Answer?
13 centimeter square per second.
Answer. Huh? Answer, ma. Value. What is the value? 26 into 0.5.
13.
13. 13.
13.00.
13 centimeters square per second. Okay. So likewise you need to find. Next. Tell me the units of this. Answer. Answer for this. Anyone? Anyone? What is the answer for this? A or B or C or D? Anyone? Units of Q by KT, ma. Anyone?
E, sir.
So much time you are taking. What are the units for Q by KT?
D, sir.
D, D wrong.
V inverse, sir.
Huh?
V inverse.
V inverse is right answer. How do you get Q by KT? Tell me. With what formula? Volt equivalent temperature. What is volt equivalent temperature? Vt is equal to KT by Q. KT by Q, what is the value of this one? KT by Q, it's a voltage. Volt equivalent temperature means what are the units? Volts. Right? It's given by V, capital V. Now, volt equivalent temperature KT by Q is V. But what it is asked in the problem? Q by KT. Q by KT. So that is equal to how much? 1 by V. That is equal to V inverse. Last time, last 2 years back, they have been asked GATE exam. Right? Q by KT is V inverse. Simple answer. Next. So that's what you please put concentration even on units also. Units are very important for us. Right? Sometimes they may be asked in units also. Right. Find the answer. Determine the thermal voltage Vt at a temperature of 127 degrees C. Answer. Answer. Anyone? Determine the thermal voltage Vt. Thermal voltage or volt equivalent temperature at 27 degrees C. What is Vt formula? Kt by Q. And substituting K and Q value, what do you get? Ty. You need to remember this one. T by 11,600. T should be in degree Kelvin. T should be in degree Kelvin, but T is given 127 degrees C. Convert into Kelvins, 273. How much? 273 plus 127. How much?
300.
400. 400 degree Kelvin. So that is equal to 400 degree Kelvin divided by 11,600. How much? 0, 0, 0, 0. Huh?
0.034.
0.03. Then 30 millivolts. 0.03, that is equal to 30 millivolts. Simple answer, sir. You should be remembering all these formulas, especially volt equivalent temperature. 0.03, that is equal to 30 millivolts. Next. Find the answer. The energy band gap of silicon at 3000 degree Kelvin is. It's one of the most important questions asked in one of the competitive exam. The energy band gap of silicon at 300 degree Kelvin is. Answer, formula. How do you find energy gap? Anyone? Tell me the formula. How do you find energy gap? Energy gap.
Eg naught
E-
minus beta
Very good.
into
Eg is equal to Eg naught minus beta into capital T. What is
beta
beta?
into
Beta into capital T. What is Eg
1.21.
naught? Eg naught for silicon is 1.21 minus. What is beta? Beta is change in energy gap with respect to
3.6
temperature.
into 10 to the power of minus 4.
3.6 kada into 10 power minus 4
4.
capital T. This is for silicon. Silicon, what is the beta value means? You should remember this 3.6 into 10 power minus 4. For germanium, what is the beta? 2.23 into 10 power minus 4. You should remember all this, right? So this is a decrement of energy gap per every degree C rise in temperature, right? So now silicon it has been asked, so therefore Eg naught is equal to 1.21 minus 3.6 into 10 power minus 4. Capital T should be in degree Kelvin, so it is also already given in the problem degree Kelvin 3000. So find the answer. Answer
0.13 electron volts.
0.13 electron volts. Good. 0.13 electron volts. After point, you need to take only 2 points, 2 values. Energy gap is equal to 0.13 electron volts. So it's been given A. A is the right answer. Okay, we'll go for next problem. Find the problem. Assume electron charge is given, kT by q is given, electron mobility is given. If the concentration gradient of electrons injected into a p-type silicon sample is 1 into 10 power 21, the magnitude of electron diffusion current density. Just now we have solved it. Just now we have solved it. Same problem, huh? No, here 2000. It's a similar question, we have already solved it. Find the answer. Answer anyone? Magnitude of electron diffusion current density means what you need to find? Jn. Jn is equal to E into dn by dx. dn is not given, you need to find. How to find it? E is given already 1.6 into 10 power minus 19. How to find dn? Dn divided by mu n is equal to Vt. That is equal to 25 millivolts. dn is equal to mu n 2000. All are given in centimeters, so no problem. 2000 into 25 milli. 2000 into 25 milli, 3 zeros, into 5 2 is 50. 50 centimeters square per second. Substituted dn is equal to 50 into 10 power 21. That is equal to how much?
8,000, sir.
8,000, right?
8,000, sir.
8,000, right? Answer is B, 8,000. Okay, next problem. Given data, anyone find the answer and tell me. In an n-type silicon sample having electron mobility mu n, twice the whole mobility, 2 times of mu p, is subjected to a steady illumination such that electron concentration doubles, means n is equal to 2 times of n. Electron concentration is given by n kada, small n is equal to, it is doubling, so 2n from its thermal equilibrium value. As a result, the conductivity of the sample increases by a factor of. So this is the given data. You need to find conductivity is subject to a steady state illumination such that electron concentration doubles from its thermal equilibrium. As a result, conductivity of the sample increases. Right. Tell me, what is the conductivity? Conductivity of n-type or p-type? N-type. Sigma n. And here it is steady state illumination. So you need to go for before illumination and after illumination. So sigma n take after illumination. After illumination. Sigma n before illumination. After illumination and before illumination. Anyone? How to do this? Answer? What is sigma n after illumination? Answer this one as sigma n after illumination. What is sigma n after illumination? Ma? What is the formula for sigma? What is for formula for sigma? J is equal to NE VE. Kada? J is equal to NEVE. J is equal to sigma E. Sigma is called conductivity. Sigma is equal to NE or NQ NE VE. Sigma is equal to J is equal to sigma E NEV. V is equal to mu E. This is NE mu E. Right. Sigma is equal to NE mu. NE mu. So this is the formula. So after illumination, I can write this one as N E mu n suffix n. After illumination. Before illumination, what is before illumination? Before illumination, the formula is same formula Ne mu n. But after illumination, what happens to the parameters mu n and n? It is being doubling. So what do you get here? What do you get here? See, mu n is equal to n is equal to 2n into E mu n. It is becoming twice that of mu p. Twice that of mu p. But again you need to find relation between mu p. But here also only mu n. So instead of changing that mu p, you please keep it like that only. 2n into E into mu n. This is after illumination. Before illumination, Ne into mu n. So sigma n after illumination divided by sigma n before illumination, that is equal to 2n E mu n whole divided by Ne mu n. Ne mu n, Ne mu n. That is equal to how much? 2. Right? So sigma n is conductivity after illumination is equal to twice that of conductivity before illumination. Before illumination is the right. It's increases by a factor of how much? 2. It is increasing by a factor of 2. See, for confusion purpose, he has given mobility of electrons is equal to twice of mobility of holes. If you substitute this one, it will become complicated. No. If you substitute here instead of mu n twice that of mu p, then it will become complicated. So let us cancel these terms because mu n you keep it like that. Mu n is there. Mu n gets cancelled. Suppose if you keep this instead of mu n, if you give twice that of mu p, then where will you go for solution of this problem? Isn't it? So for confusion purpose, you will be giving like this. So why to go for confusion? Just simply cancel out mu n and mu n. Mu n and mu n cancel out. N cancels. So it's equal to 12. Sigma n after illumination is equal to 2 times of sigma n before illumination. So answer is twice. Got it? So this is one of the important topic, carrier lifetime. Carrier lifetime means it's a similar to that of a human lifetime. Human being lifetime. Human being, he takes his birth, he or she takes his birth, and the starting point of birth to death or expired. So in between this region, the region between birth and expiry date is nothing but lifetime of human being. Lifetime of human being. So similarly here also, what is the lifetime of a charge carrier? It may be electron or it may be hole. Suppose electron is there. Electron, while it is revolving around the nucleus at outermost orbit, it takes energy from the atmosphere. It jumps from valency band, because this is valency band. It jumps from valency band means now it is taking birth here. And it is jumping from this point to this point. And if it is finding a hole in the atmosphere, this electron goes and fill into this hole. So then if it is going and fill in this hole, then it expires. Right. Here it is taking birth. Here while it is filling into the hole, it is expiring. And this is also called recombination. Electron and hole recombination. So what is the lifetime? What is the time taken by the charge carrier to take its birth and to expire? That difference of time period is called carrier lifetime. Because we are calculating a lifetime for what? Carrier. It may be electron or it may be hole. So therefore, what is that carrier lifetime? Lifetime means what? The time taken by the charge carrier to take its birth and to get recombined with the hole. That time is called as carrier lifetime. And that is given by a formula here, which is called L. L is called diffusion length. L is called diffusion length. D is called diffusion constant. Tau is called carrier lifetime. So what do you get? Suppose carrier lifetime of holes means, what is the formula? LP is equal to square root of dp into tau p. So therefore from this Lp square is equal to dp into tau p. So tau p is equal to Lp square divided by dp. This is the formula for calculating a carrier lifetime of holes. Similarly, what is carrier lifetime of electrons? Tau n is equal to ln square divided by dn. Ln square divided by dn. This is carrier lifetime of holes and this is carrier lifetime of electrons. Okay, so remember, time of hole is directly time carrier lifetime of any charge carrier, it may be electron or hole, depends on diffusion length of its carrier. Tau is directly proportional to diffusion length of holes or diffusion length of charge carriers. It may be holes or it may be electrons. How much length it is traveled, time is also increasing. Time increases, length increases. Length decreases, time also decreases. So this is an important point you need to remember for carrier lifetime. Right?